Hello and welcome to this channel. We'll be taking a close look at the Ensemble Kalman Filter for reservoir characterization. It's one of the most important tools when you want to assimilate data as and when they become available. So in theory, we're trying to recover some true but unknown, say, permeability field. So we first construct a suite or an ensemble of reservoir models. These are all conditioned to previously acquired data, which consists of geologic interpretation, well-log data, core data, and perhaps even seismic data. Typically, we work with an ensemble size of about 30 to 100 members. We run each one of these ensemble members through a reservoir simulator up until the time that an observation becomes available. In this plot, you're looking at oil rate versus time, and we're making the assumption that we have an observation from the field at a time of 10 days. And you can see that there are discrepancies between the model predictions and the observations, and we want to modify the permeability and the porosity field uh, using these discrepancies. So how do we do that? Well, first we collect the state variables associated with each and every ensemble member. This includes the grid block permeability values, the grid block porosity values, grid block pressure values, and saturation values. So for each ensemble member, we have a collection or a vector of these different values. And for an ensemble of models, we're going to have an ensemble of state vectors. And this is what we're going to be using as an input to the Ensemble Kalman filter. One additional detail is that we also add the model predictions to the end of the state vector. If you look at the vector on the right, we have the model permeabilities, porosities, pressures, saturations, and finally we have the model predictions. So this constitutes our state vector x sub I for ensemble member I. Let's take a look at the Ensemble Kalman filter equation. We have the state vector for ensemble member I. We have the cross covariance between the ensemble model predictions and the state variables. We have the covariance between the ensemble member predictions. We have the noise covariance matrix, which controls which observation you're going to trust to make an update. If you have a noisy measurement, you're going to trust it less. If you have a measurement with high resolution, you're going to trust it more. We have our observations, and we finally have our model predictions for each and every ensemble member. So we update our state vector for ensemble member I and get the updated state vector by using the discrepancy between the model predictions and the observations denoted by Y. And all the matrices in the middle constitute what's known as the Kalman gain matrix. And although we are not going to be taking a deep dive into the mathematics, the Kalman gain matrix essentially functions like the cross covariance between the state variables and the model predictions. So if you were to plot the model predictions versus the state, any given state variable, in this example I'm just showing you some arbitrary pressure value in grid block 3 for each one of the ensemble members, you can see that there is some relationship between the model predictions and the uh, ensemble member state variable values. And if you get an observation that's denoted by the red dot, then essentially you know that if you adjust the pressure in grid block 3 for each one of the ensemble members towards the right, or if you increase them, then our model predictions are going to be matching our observation. And we do the same for all the other state variables within our ensemble. So when we apply this update using the cross covariances, we are going to be updating the uh, ensemble members individually, and so we have an ensemble member average at a specific time, and we'll also have an updated average at the same time. So we use this updated average permeability field and conduct a simulation uh, from uh, the time when we stopped till the next observation becomes available. So again, we're trying to reconstruct the true but unknown permeability field. We now have an updated ensemble at a time of 10 days, and we run each and every one of these ensemble members in a simulator from the time of 10 days to the time of 20 days when our next observation becomes available. And now you can see that the model predictions are a little bit tighter and centered around the observations simply because we've already made one update. We again collect all of the state variables for each and every ensemble member that comprises the permeability field, porosity field, pressures, and saturations. And you can see that the state vector again contains the vector of grid block permeabilities, grid block porosities, grid block pressures, saturations, and the model predictions at a time of 20 days. That's the time at which we're making our update. And we still have the ensemble member I denoted by X sub I. We apply our update, and again we have a permeability field and a porosity field before the update at 20 days, and when we apply the update we have an updated permeability field and porosity field and pressure and saturation field as well, because we're updating the entire state vector. So this is the updated state vectors at a time of 20 days, and we will have the corresponding ensemble members updated at that time of 20 days. And hopefully these ensemble members are approaching closer to the true but unknown permeability field. Next, we run these ensemble members from a time of 20 days to a time of 30 days when the next observation becomes available, and repeat this entire process again, where we collect the state vectors for each and every ensemble member at a time of 30 days, perform an update, and uh, at a time of 30 days, we now have the updated set of ensemble members. And with this updated set of ensemble members, we can run a series of forecasts and update them again when data becomes available. Something to keep in mind in this whole discussion is that I have avoided a discussion of the uh, formulation of the Ensemble Kalman filter equation. I've also avoided a discussion of a few of the challenges associated with frequent data assimilation with small ensemble sizes. One of the things to keep in mind is that since we are using cross covariances between the model predictions and the state variables to perform an update, and that's a statistical quantity, the more number of ensemble members we have, the better is our estimate of those statistical quantities. Unfortunately, that also means that we would have to run many more simulation models, and that can be computationally expensive. So we typically run with an ensemble size of between 30 to 50 models, and there are ways by which we can ensure that we are restricting the updates to meaningful regions within the reservoir. And those topics are associated with a concept called covariance localization, which is out of the scope of the present discussion. But I hope you enjoyed this introductory lecture on ensemble based data assimilation for reservoir characterization.